You think of the atom as a tiny solar system. Electrons orbit the nucleus like planets around the sun. You imagine neat rings, predictable paths, a miniature cosmos you can almost picture. It feels intuitive. It feels right. But it's not. It's wrong. You think you can track an electron. Know where it is, know where it's going. You think the universe is orderly at that scale, that it obeys the same rules you see every day. You're comfortable with that picture. Too comfortable. And that comfort, it blinds you, because the truth doesn't orbit. It doesn't follow paths. It doesn't fit your expectations. And nothing you think you know about the tiniest particles survives the moment you look closer. Not your models. Not your intuition. Not even your certainty. You've seen it in textbooks. A tiny nucleus at the center, electrons spinning around it like planets on invisible tracks. It's tidy. It's comforting. You can almost imagine it in your mind's eye. You think you understand it because it mirrors the world you live in. The sun orbits, the moon orbits, planets spin in neat paths. So why wouldn't the same be true for atoms? This is wrong. The truth is that electrons do not trace paths. They do not move like billiard balls around a table. You cannot take a snapshot and pinpoint their exact location while simultaneously predicting where they will go next. Classical physics, the physics that governs your everyday intuition, tells you otherwise. It insists on continuity, on predictability. Drop a marble into a bowl, and it rolls smoothly. Give it a push, and its trajectory is fixed, calculable. Electrons, at the atomic scale, refuse this law. You might think, surely if I could see closely enough, I could watch an electron orbit. But even that thought is flawed. Experiments in the early 20th century revealed phenomena that directly contradicted the neat solar system analogy. Atoms emit light not continuously, as a spinning electron should, but in discrete packets. If electrons were orbiting like planets, light would bleed out in a smooth, unbroken stream. It doesn't. It appears in sudden bursts, precise jumps. The universe itself seems to mock your mental picture. Think about it. You're relying on sight, on analogy, on what makes sense in the macroscopic world. And yet, at the scale of the atom, all of these crutches crumble. The electron's behavior cannot be captured by simple imagery or classical reasoning. This is more than a minor correction. It's a foundational failure of intuition. What you thought you knew about motion, about continuity, about the very idea of an orbit is irrelevant. Even physicists felt this unease. Rutherford's nuclear model, the closest thing to your imagined solar system, placed electrons around a tiny, dense nucleus. But when they tried to make the numbers work, calculating how electrons should radiate energy and spiral into the nucleus, they ran into a wall. Classical mechanics predicted catastrophe. Electrons should collapse into the center almost instantly. Reality did not comply. Atoms were stable. Stable despite what the math or your intuition said. This is the first crack in your worldview. You think you can picture reality. You think you can predict it. You cannot. Electrons are not planets. They do not orbit. The image in your head is comforting, but it is fundamentally false. Bohr did not create this discomfort. He merely formalized it, gave it language, and showed that embracing it, rather than resisting it, is the only path forward. Your mind wants neat paths, smooth motion, continuity. Nature laughs at this. And the deeper you look, the less your classical intuition serves you. You're about to leave behind the solar system analogy, and with it, the certainty that reality behaves like anything you've ever experienced. You're still clinging to the idea of smooth motion. You imagine electrons drifting gently around the nucleus, their energy flowing continuously, like planets accelerating or decelerating as they swing through space. It feels natural, it feels inevitable. But this is wrong. Bohr introduced a radical idea. Electrons cannot possess arbitrary amounts of energy. They exist only in discrete energy levels, fixed rungs on a ladder of possibility. No sliding, no gradual changes, no in-between. You cannot take a small step from one orbit to another. You cannot nudge an electron gently upward. The universe forbids it. Energy is quantized. Think of it as climbing a staircase. You can stand on one step or the next, but there is no midway point. You cannot levitate between steps. You cannot exist in a fractional state. And yet, your intuition screams otherwise. In the macroscopic world, motion and energy are continuous. You pour water into a glass. The level rises smoothly. A car accelerates gradually. Electrons do neither. This alone is jarring. But the implications are more profound than you might imagine. If an electron cannot occupy an intermediate energy, then the transitions between levels cannot be continuous either. When an electron absorbs or emits energy, it does so in discrete jumps, not smoothly, not predictably, not in a way that matches any classical analogy. Imagine an electron leaping instantaneously from one orbit to another, vanishing from one state and appearing in the next with nothing connecting the two. You picture a line, a curve, a gradient of motion, but reality provides none. And here's the unsettling truth: you have no way to see these jumps directly. All you have are the consequences. Spectral lines, bright lines in a dark field. The fingerprints of electrons leaping across energy levels. Each line a silent, unbroken testimony to the absurdity of your classical expectation. The smooth paths you imagine dissolve into a scatter of discrete possibilities. Even worse, these energy levels are not arbitrary. They are dictated by the nucleus, by the charge of the proton, by fundamental constants you cannot intuitively grasp. The latter exists, but you cannot construct it from everyday experience. You cannot predict the step heights from your gut. Nature, at this scale, has rules of its own, and they defy your sense of continuity. So here you are, still holding a mental picture of a calm, orbiting electron. But each jump, each spectral line, each forbidden intermediate state reminds you that this picture is useless. Classical reasoning, the logic of billiard balls and planets, has no purchase here. The world is no longer a smooth river, it is a staircase of impossibilities, a sequence of rigid, quantized states. This is the first clear break from intuition. Continuity is gone. Motion is not what you think it is. Energy does not flow, it leaps. And once you accept that, once you confront the absurdity of electrons hopping impossibly across voids, you are ready for the next shock, the way they interact with light, another domain where your expectations collapse entirely. You still picture the electron as a tiny planet, spinning predictably, moving smoothly. Even with quantized energy levels, you might convince yourself there's some continuity you haven't seen yet. Perhaps energy flows invisibly, perhaps light emission is just a minor side effect. That too is wrong. Electrons do not simply orbit, they communicate with light in ways that shatter classical expectation. You imagine radiation as continuous. A spinning electron should leak energy, gradually producing a soft, unbroken glow. But atomic spectra tell a different story. Light emerges in discrete packets, each photon an indivisible unit, a sudden manifestation of energy. The universe does not whisper, it snaps. Consider a thought experiment. You excite a hydrogen atom, nudging its electron into a higher energy state. Your intuition says the electron should glide back down, radiating energy along the way like a sliding marble losing speed on a ramp. But that does not happen. The electron waits, suspended in its quantized orbit, then instantaneously it drops. A photon appears, a single discrete burst of light. There is no intermediate glow. There is no gradual descent. Even more unthinkable is absorption. Shine light of the wrong frequency, and the electron ignores it. Shine the exact right frequency, and the electron snaps to a higher state. Energy is not just quantized in the electron, it is quantized in the interaction itself. The act of exchange, the very coupling between matter and light, is governed by rules that defy any analogy to your macroscopic intuition. Continuous waves, smooth accelerations, gentle flows, they do not apply, and yet we can measure it. Spectral lines are the proof. Each bright line, each missing dark space encodes the electron's impossible leaps. You cannot see the jump itself. You only see the effect, a silent, rigid signature of nature's refusal to conform to your expectations. The smooth classical world collapses, replaced by discrete, binary events that are absolute and unyielding. At this point, the universe no longer behaves like anything you've experienced. Electrons do not radiate gradually. Light is not a constant drizzle. Energy is not a continuum. Every intuition you brought from the everyday world, the way objects move, the way energy flows, fails here. You are approaching a conceptual precipice. The electron is no longer a particle obeying the laws you know. It is a participant in a system whose behavior is dictated by the rigid, unforgiving rules of quantization. And once you confront this, you are forced to confront an even deeper limitation, that reality at the atomic scale cannot be fully observed, cannot be fully captured by your senses, and cannot be made to behave in ways that satisfy your desire for continuity. You still think you could watch the electron if only you had a powerful enough microscope. You imagine freezing it in place, tracking its motion, plotting its orbit, and verifying Bohr's model with your own eyes. This is wrong. At the atomic scale, the very act of observation changes reality. You cannot measure an electron's position without disturbing it. You cannot know its motion without affecting it. The classical belief that measurement reveals truth, pure, undisturbed, objective truth, is shattered. Reality refuses to be pinned down. Every attempt to see more clearly alters the thing you are trying to see. Imagine trying to photograph a firefly in a dark room. To see it, you flash a light. The light startles the firefly, it moves differently. Now imagine doing this on a scale 1,000,000 times smaller, with particles that respond to the faintest disturbances. Your camera is not passive, it nudges, it kicks, it forces the electron into states it might not have chosen. Measurement and existence are intertwined. The boundary you assumed between observer and observed dissolves. Even more unsettling is that there are limits to what you can know simultaneously. You might try to track both position and motion, hoping to recreate the neat orbits of classical physics. But nature will not allow it. The more precisely you fix one, the more uncertain the other becomes. The universe imposes a fundamental fuzziness, a barrier that no technology, no clever experiment, no intuition can overcome. This is not imperfection or human error, it is law. Bohr's model, in its quiet authority, acknowledges this. Electrons exist in defined energy levels, but the paths they take are fundamentally unknowable. You can calculate probabilities, predict outcomes statistically, but the smooth certainty of classical trajectories vanishes. You cannot picture the orbit, cannot freeze it in a frame, cannot watch it like a planet around the sun. Your mind wants continuity, predictability, visibility, but nature does not comply. This is a profound shift. You are forced to abandon one of the deepest crutches of intuition, that knowing requires seeing, that reality conforms to observation, that objects have defined states, independent of measurement. None of these are true at the atomic scale. Reality becomes elusive, probabilistic, resistant to classical logic. And yet, there is structure, there are rules, there is quantization, there are spectral lines. But these rules are abstract, invisible, and counterintuitive. They describe patterns of possibility rather than continuous motion. The electron is not somewhere in a classical sense. It is a set of potentialities constrained by the architecture of the atom. By the end of this chapter, the comforting image of electrons as tiny planets has crumbled completely. Classical mechanics cannot capture them. Your intuition fails. Observation cannot rescue it. You are left with a world that is partly knowable, partly unknowable, and profoundly resistant to the mental pictures that once gave you confidence. This is the point where Bohr's insights begin to seem inevitable. You are standing at the edge of a new logic, one in which probability, measurement, and quantization replace certainty, continuity, and deterministic paths. And yet, the most radical consequences are still ahead. By now, your comforting mental models, the tiny solar system, smooth orbits, continuous motion, have all collapsed. You understand that electrons do not orbit like planets. Energy is quantized. You accept that light is exchanged in sudden bursts. And yet something more disorienting awaits: the rules themselves. Bohr did not offer a visual model to make electrons easier to picture. He offered postulates, axioms that defied classical mechanics, stripped of intuitive explanation, and accepted purely because they worked. The first postulate is simple in words, but radical in consequency. Electrons can exist only in certain discrete orbits without radiating energy. Stop. Think about that. Classical physics predicts that any accelerating charge, like a spinning electron, should radiate continuously. Bohr says it doesn't. Atoms are stable. Full stop. Your mind resists. How can something charged spin without emitting energy? How can motion persist without decay? Classical reasoning screams that this is impossible, yet nature complies. The electron stability is not a gradual balance of forces. It is absolute. dictated by postulate. You cannot derive it from intuition. You cannot reason your way to it. You must accept the fact first and understand its consequences later. The second postulate is even stranger. Electrons jump between these orbits, and the energy difference appears as a photon. There is no continuous path, no smooth emission. The electron does not slide down. It vanishes from one orbit and appears in another. And that photon, it is not a byproduct, it is a discrete, measurable unit of energy. Nature's bookkeeping is rigorous, brutal, and indifferent to human notions of continuity. Bohr's postulates shatter more than classical trajectories. They undermine determinism itself. Cause and effect, as you once knew them, no longer hold at the atomic scale in the intuitive sense. You cannot predict the precise moment of a jump, only the probability that it will happen. Certainty is replaced by structure, a lattice of possibility that obeys rigid rules rather than continuous laws. Consider the philosophical implications. Energy conservation still applies, but in a form divorced from the gradual changes you imagine. Motion exists, but only in quantized bursts. Electrons exist, but only in probabilistic states that defy visualization. Bohr's rules force you to accept a universe where the classical crutches of intuition are irrelevant, where the familiar scaffolding of cause, trajectory, and continuity is dismantled. And yet, the postulates are elegant in their minimalism. They describe the hydrogen atom almost perfectly. With two assumptions, Bohr accounts for spectral lines, stability, and energy exchange. This is the paradox. The rules are simple, yet incomprehensible to intuition. They are the first step in a framework that reconciles the strange, jumpy, elusive behavior of electrons with observable phenomena. Here, at this stage, you confront the radical nature of modern physics. The laws of reality at small scales are not merely unfamiliar, they are fundamentally at odds with the experience you carry from the macroscopic world. Stability arises without continuous motion. Light emerges without gradual flow. Electrons exist without defined paths. And Bohr's postulates are the bridge, a minimalist map over a chasm your intuition cannot cross. You are standing at a conceptual cliff. Beyond it lies the further abstraction of probability clouds and orbitals, a place where your remaining classical assumptions will be stripped away completely. Bohr has guided you this far, but the real leap, the one that forces the mind to truly reframe reality, is still ahead. You are now fully aware that electrons do not orbit like planets. You know energy is quantized. You understand that light appears in sudden bursts, and that observation itself disturbs reality. Classical intuition has failed at every turn, yet even this is not the final step. The real challenge is to let go of visualization entirely, to abandon the crutch of imagining electrons as objects, moving along paths. Bohr's model still uses orbits as a tool, a compromise between classical imagery and quantum behavior. But these orbits are symbolic, not literal. Electrons do not trace neat curves. They exist as probabilities, as patterns of potential spread across space. To grasp this, you must relinquish the idea that you can picture the atomic world with anything resembling familiarity. You must think abstractly, in terms of likelihood rather than trajectory, in terms of clouds rather than points. Imagine an electron not as a particle, but as a cloud of possibility. In some regions, it is likely to be found. In others, almost impossible. The edges of this cloud are not walls but gradients, representing diminishing probability. The electron does not travel through space, it exists in space. Motion, as you once understood it, no longer applies. Your mental image of a planet circling a sun is now a hindrance, a trap that prevents understanding. This abstraction dissolves yet another intuitive belief, that atoms are small solar systems you can map visually. They are not. They are dynamic systems defined by rules, by constraints, by probabilistic envelopes. Bohr's quantization is the first hint, but the full leap is to recognize that reality is not a picture you can draw. It is a structure of possibilities, a lattice of probability, a set of patterns in which matter only sometimes behaves as a particle, and sometimes as something else entirely. Think about the consequences. If the electron is a cloud of potential, then interactions with light, with other atoms, even with measurement devices, are encounters with probability distributions, not solid objects. Predictability is statistical, certainty is replaced by expectation, and causality is softened. The world has become a landscape of abstractions where every classical crutch, motion, trajectory, energy flow is transformed into a rule about potentiality rather than actuality. This is what Bohr's model truly initiated, a new way of thinking. It is not merely a different diagram of the atom. It is a conceptual revolution. It forces you to abandon visual intuition, to reason without the safety of everyday analogies, to confront the stark difference between the world as it appears and the world as it exists at the atomic scale. The comfortable solar system. Metaphor, the smooth orbits, the flowing energy, they were never real. They were scaffolding, necessary only until you could step beyond them. By embracing abstraction, you begin to see atoms as they really are, systems governed by rules that demand a departure from classical logic, from causality as you know it, from motion as you perceive it. Electrons become expressions of probability, energy exchanges become discrete events, and the quantum world asserts its independence from your intuition. At this stage, the mind begins to expand. Reality is no longer a series of neat, continuous events you can picture. It is a set of constraints, a lattice of possible outcomes, a cloud of potentialities, beautiful in its rigor, alien in its defiance of expectation. And in that alienness lies a deeper philosophical truth. The universe is not obliged to make sense in ways that satisfy the human imagination. You have abandoned the comforting illusions. Electrons do not orbit like planets. Energy is quantized. Light is exchanged in discrete bursts. Observation changes reality. Electrons exist as clouds of probability, patterns of potential, not as classical objects. By now you might think you have reached the edge of comprehension, but Bohr's model forces one final confrontation, the profound unknowability of the universe itself. You assume that if only you had enough information, enough precision, enough clever instruments, you could map reality completely. That assumption is wrong. Bohr showed that at the atomic scale, certainty is not merely limited, it is fundamentally inaccessible. The rules that govern the behavior of electrons and atoms do not yield to visualization, intuition, or even imagination in the classical sense. Nature does not simply hide, it structures reality in a way that forbids complete knowledge. Consider this: even with perfect measurement, you cannot simultaneously know everything about an electron. Its position is blurred, its motion is probabilistic. The more precisely one property is pinned down, the more uncertain the other becomes. This is not a flaw in technique, not a limitation of tools. It is a law of nature. The atom is not a miniature machine with hidden gears waiting to be exposed. It is a system defined by constraints and possibilities, a domain where certainty is replaced by probability and predictability is statistical, not absolute. And yet, this unknowability is not chaos. It is structured. Spectral lines, quantized jumps, energy levels, they are precise, measurable, and repeatable. The universe imposes strict rules, but the rules operate in a domain where your classical intuition fails. Cause and effect remain, but only in terms of likelihood. Motion exists, but only as a range of possibilities. Stability exists, but not as a smooth trajectory. You begin to realize that the universe is coherent, but coherence does not require you to comprehend it directly. This is Bohr's ultimate gift and his ultimate challenge. He forces you to confront a universe that is both knowable and unknowable, predictable and inherently mysterious, governed by strict rules yet defiant of direct visualization. The atom is no longer a miniature solar system. It is a landscape of potentialities, a structure of probability, a domain in which your intuition is irrelevant. To engage with requires acceptance, abstraction, and a profound shift in perspective. The philosophical consequences are staggering. If the smallest constituents of matter behave in ways that defy classical logic, what does that say about the universe as a whole? If your senses and intuitions, honed over millions of years of macroscopic experience, fail at the atomic scale, how much of reality is forever inaccessible to the mind that trusts them? Bohr's model does not merely change physics, it changes the way you must think about knowing itself. It imposes humility on your understanding, and yet in this unknowability there is awe. In the rigid, counterintuitive rules, there is beauty. The universe does not cater to human intuition, yet it is coherent, elegant, and precise. Electrons, photons, energy levels, these are not chaotic anomalies. They are glimpses into a deeper order, a structure of existence that operates independently of your expectations, yet consistently enough that it can be studied, measured, and even partially comprehended. Bohr's atom, in its quiet defiance of classical intuition, leaves you suspended between certainty and mystery. You see the limits of your knowledge, the impossibility of direct visualization, the futility of trying to picture atomic reality. And in that suspension, there is wonder. The universe is no longer a machine to be fully grasped. It is a domain of patterns and rules, a place where probability reigns and imagination falters. It is unknowable, yet beautifully, inevitably structured. This is the final lesson Bohr offers. The universe is not obligated to make sense in ways that satisfy human intuition. And once you accept that, once you see the quantum world as it is, not as you imagine it, the mind opens to a kind of philosophical awe that no classical picture could ever inspire.